Okay, so as you guys have noticed, I uploaded the second project in iCampus. So for this second project, we are not going to use the university database schema. So instead, you need to go to this directory, home SW3003 movies. And inside this directory, you can find schema.sql. If you run that schema.sql, it will create these tables with these columns. And then to load some, to insert some data, to insert some records into those tables, you need to run these statements. Copy statement is for Postgres to read a text file and insert each individual record into the given table. And once you initialize your tables, you need to write a SQL queries for the following 10 problems. And as you can see, each question, each problem has a title. So you need to use these features in your SQL. Okay. Of course, you can write your query without using with clause, but this assignment is for practice. You are going to gain some hands-on experience on these constructs, advanced, intermediate level SQL constructs. So you must use these constructs like with, nested query, correlated query, and so on. Okay. And if you want, you can get some help from AI. But before you get help, you should try to solve these problems by yourself. When you have a hard time, of course, you are free to get some help. So last semester, I gave similar problems, and most of you guys got almost perfect scores for all three SQL assignments. So I believe these problems are not too difficult, but it is not also too easy. So I hope this will be a good practice for most of you guys. And if you have any question about these problems, you are welcome to ask questions in Piazza website. And what's the second one? Okay, so I also uploaded some exam problems from last year. And if you check these problems, you may find the spring exam was much harder than fall exam. Sometimes I fail to control the difficulty level, so I don't know how it's going to be this semester. So anyway, so the grading will be done based on your relative performance compared to other students. So even if it's even if it's very hard, I guess no need to worry too much about that. And also, while you are solving these problems, you may find some problems are ambiguous. If it's not clear, then you can make your own assumption, and maybe also you can get some help from AI tools. So I strongly recommend you guys to check your own answer using AI tools. And for SQL problems and relational algebra problems, there can be many different correct answers. Also, you can check whether your answer is correct or wrong using those AI tools. I wish maybe sometime soon our university will develop some AITA system, teaching assistant system. So if you submit your programs or homeworks, then AI tools will grade your project, and also you can get some feedback from those AI tools. I guess it's not too long.
Can you share the date on the grade for the midterms for the previous semester, like all the media?
You mean grading curve or the distribution of the score? Okay, I will think about that. Yeah, I got a question from one of the students in Piazza website, so I fixed it. So you should try, maybe I can try now. Oh, what I'm doing. Come on. Okay, it works now. So you should run it again. Any other question? And as I announced, the exam will be on 22nd Wednesday, and I will announce the location when it's confirmed from the department later. All right, then let's move on to normalization theory. So last time we learned some functional dependency rules. So when you get some number of rules, you can expand the set of the rules by using union, decomposition, transitivity, and so on. And once you finish, once you cannot add any additional functional dependency to the set, you are done. And we call that large set closure of functional dependencies. And from today, we are going to learn how to decompose a bad table into good, well-designed tables. We call that process, we call that procedure decomposition. And suppose you had a large table T, and for this table T, you got some number of functional dependencies. Something like this. And then suppose you decompose this large table into T1 and T2. And some rules can be applied to T1. Let's label it A goes to B. A determines B, and let's say C determines D, and let's say there's another one, B determines C. Right. So and let's suppose this table T1 has attribute A and B, and table T2 has attribute C and D. Then you can take this rule, you can take this functional dependency from the original functional dependency set. And for table T2, you can take the second functional dependency. But what about this? B determines C. Since table T1 doesn't have a C and table T2 doesn't have B, you cannot include this functional dependency in either of these two tables. But sometimes it is okay, sometimes it is not. And to check whether this decomposition didn't lose any functional dependency set, you should compute the closure. So from the functional dependency set for T1, and also for this table T2, you have this functional dependency C determines D. And using these two functional dependencies, you should compute the closure. Then some additional functional dependencies like A determines A, AB determines B, something like this. You can add lots of functional dependencies to this closure, and you also do the same for the original functional dependency set. So if the closure of the original functional dependency set is equivalent to functional dependencies of the decomposed functional dependency set closure, then we say we didn't lose any functional dependency. But in this particular example that I draw in this slide, we lost this third functional dependency. No matter what functional dependencies you add, we cannot restore this last functional dependency. Then we say this decomposition doesn't preserve functional dependencies. Okay? All right, that's the fundamental, that's the basic to learn this BCNF and 3NF. What is BCNF? To to check whether your table is in good shape or in bad shape, you need to check each functional dependency for your given table. And if all your functional dependencies satisfy one of these two conditions, then your table satisfies BCNF condition and your table is in good shape. It is in good design. So what is these two rules? It's about superkey. If suppose you computed closure of your functional dependency, and let's take each functional dependency from this set, and if each functional dependency is trivial, it is good. And also, if it is not trivial, then you need to check whether the left term is a superkey of the given table. If so, your table is in good shape. Your table satisfies the BCNF. We call this left term determinant, and we call this right term dependent. So if determinant is superkey of your table, then your table is in BCNF. Okay? No need to worry about this first rule, it's so trivial. Nobody cares about trivial functional dependencies. So most of the time, you just need to check whether the determinant, whether the left term of this arrow is a superkey or not. If left side is a superkey, then your table is in BCNF. So let's look at an example that is not in BCNF. Instructor department. We combine the instructor table with the department table. So ID determines name and salary and department name. Department name also determines building and budget. Using transitivity rule, we can say ID determines building because ID determines the department name and department name determines building. Therefore, we can say ID determines building and ID determines budget. So here in this table, it seems ID is a candidate key, and ID along with the department name seems to be a super key. It doesn't seem to be, it is minimal. So let's consider this functional dependency. Department name determines building and budget. Is this trivial? No, it is not. Left determinant is different from right dependent. So this is not a trivial dependency. And we should check whether this left determinant is the super key of the table. Is it super key? No. Department name alone does not determine name of the instructor. It doesn't determine salary of the instructor. There can be multiple records with the same department name. Therefore, department name alone is not a super key, and that is why this table is not in BCNF, and this table is considered bad. It is bad design. Is it clear?
You can also think ID is the key of building and budget, and the case is, I think it is BCNF because
ID determines building because department name determines building as well.
yeah, so
So,
in transitivity
Mhm.
rule, ID also key of the building and budget, and in the term of this operation, I think it is okay for BCNF. Is it clear?
No. Department name is the problem. Department name determines building. So building is dependent on department name, right? So department name is not a candidate key in this table, but it determines some other attributes of the table. That is the problem. Why we have the problem? Because we combine the two different tables into the single one. That is what makes this table design bad.
But you can also think buildings determine its ID.
How come building determines ID? ID can determine building, but building doesn't determine ID. Even if we know the building information, we cannot tell we cannot tell the ID of the instructor because there can be so many instructors in the building, right? So key should identify a unique record in the table. And in this table, department name alone cannot uniquely identify any record in the table because there can be multiple department names, duplicate department names in the same table. Okay? Question?
In BCNF, all the functional dependencies of determinant should be a super key. In this case, that name can be a so it can be a
Correct. So yeah, the left side of the functional dependency must be a super key. If that is true, then we say the table is in BCNF. Okay? Easy. Okay. So suppose we found that a table is not in BCNF. So we need to decompose it. How can you do that? The rule is given here. So pick a functional dependency that violates BCNF condition. And we will create new tables, 2 new tables. Include determinant and dependent attributes in the same table. That is the first table. And for the second table, we will deduct alpha from beta. Usually you may assume that left determinant left determinant doesn't show up on the right determinant. Let's suppose you have a functional dependency like this. If you find this functional dependency violates BCNF, then just remove those duplicate attributes from both sides, and then from the original table, you just deduct dependent attributes. You just choose the right one and delete it from the original table. That is going to be your second table. Okay? So in the previous example, we had a problem for this functional dependency. Department name determines building and the budget. And we don't have a duplicate attribute on both sides, so we don't need to worry about this minus alpha. You can ignore it. Then the first table will be, first table will include all these 3 attributes. And second table we deduct building and budget from the original table. That's going to be the second table. So let's go back to the previous slide. So we found a problem. What do we do? Delete these 2 attributes from the original table and create another table with these 3 attributes. So this department name will show up in the 2 output tables. And using this department name table, we can join the 2 tables to restore this large table, right? That is how BCNF decomposition is done, and that algorithm is listed as a pseudocode in the next slide. And I'm not gonna read these lines. Let's move on. But then people found that this BCNF is too strong. To satisfy BCNF, we need to decompose too much. And after decomposition, we found that so many tables need to be joined. And join is a very expensive operation. So people wanted to weaken the BCNF condition, and they came up with another normalization theory called 3NF, third normal form. So why is it too strong? An example is listed in this slide. Suppose we combine the department table with advisor table. So we have student ID and instructor ID. It seems these two attributes are from advisor table. And we have a department name and instructor ID. Let's label these two. So student ID and instructor ID, these two attributes are from advisor table, and instructor ID and department name is from the department table. And in this depth advisor table, we have these functional dependencies. Instructor ID determines the department name, and student ID and department name determines instructor ID. So what is the super key? What is the candidate key? What is the primary key of this depth advisor table?
Maybe student ID.
Hmm?
Maybe student ID, SID.
SID and instructor ID, department name. If we know student ID and department name, can we uniquely identify an instructor's ID? No. Okay.
No, student ID and then name, then can identify.
Oh yeah. Sorry, I got confused. Yeah, you are right. I mean, the first student got it right. So and let's assume we got these functional dependencies. I mean, these functional dependencies are given. So if we know student ID and department name, we can identify instructor ID. Let's assume that. And is it true? Advisor. So maybe we have this constraint saying that each student can be advised at most one instructor from each department. If we have such constraint, maybe this functional dependency will be true. Okay, let's assume that condition. And instructor ID should belong to at most one department. So instructor ID determines the department name. Okay, so we got these two functional dependencies, and let's check. Instructor ID is the super key. Oh. Instructor may advise multiple students. So instructor ID is not a super key. What about SID and department name? If we know SID and department name, then we know instructor ID. So if we know these two attribute values, then the rest, I mean, the third attribute will be known. Therefore, SID and department name is the super key. Actually, it is a primary key, candidate key of this table. So this second functional dependency satisfies BCNF condition. But this first functional dependency doesn't satisfy BCNF. So what do? We need to decompose it. How can we decompose it? So this is the problem. So we will take instructor ID and department name for one decomposed table, and we need to remove the right dependent from the original table. So here we have original table and department name must be gone. So the second table will be SID and instructor ID. Okay. Are we done? Did we lose functional dependency? Yeah, it seems so. So So for this first functional dependency, let's label it as FD1. FD1 can be included in this first table. Let's call this table X, and let's call this table Y. So FD1 is preserved in table X. What about the second functional dependency? Let's label it as FD2. We don't have a department name in Y. And in X, we don't have SID. SID is missing in X. Oh, we have a problem. FD2, this functional dependency was lost by this decomposition. So this BCNF doesn't preserve functional dependencies in some cases. So this decomposition is not dependency preserving. Therefore, people wanted to weaken the condition of BCNF, and they proposed 3NF. And the key idea of 3NF is that it allows some redundancy. And the reason why we wanted to decompose a table is because we wanted to avoid any redundant information in a table, right? Redundancy requires lots of disk space, and it makes the transactions run slow because a transaction may need to update multiple records atomically. So redundancy is bad, but if you use BCNF, if you design your table in BCNF, you can eliminate the redundancy. But if you design your table in BCNF, you may lose some functional dependencies. And you may you may hurt some semantics of the applications. And in that case, there is no option, no other option. We have to allow redundancy in the table. In that case, you can use third normal form. So 3NF always preserves functional dependency. Therefore, when you join the decomposed table, you will lose nothing. You can always restore the large table without losing anything. And this slide shows what is the third normal form. It is very similar. It is very similar to BCNF, except one additional condition. The first rule is about trivial condition. If both, if left determinant and right dependent are the same, then that functional dependency is trivial. And if the left determinant is a superkey, that makes the table in BCNF. And we have one additional condition. If these two rules are not true, we need to check this last condition, saying that each attribute in beta minus alpha is contained in a candidate key. Oh, what does this mean? Again, no need to worry about this minus alpha. Once you eliminate the redundant attribute from both sides, you guys don't need to worry about alpha. Just look at beta. And you need to check whether this beta is a prime attribute. What is a prime attribute? You guys, I didn't explain what is a prime attribute so far. So suppose you found some candidate keys. Let's suppose these three attributes form a candidate key. Then each attribute is called candidate key. Each attribute is called the prime attribute. This is a prime attribute. So prime attribute is basically a member of candidate key. Prime attribute is an attribute that consists of candidate key. Oh, it's the other way, sorry. Primary key consists of prime attributes. I'm sorry. So let's say we have X, Y, Z, and candidate key needs all three attributes, then X is a prime attribute, Y is also prime attribute, and G is also prime attribute. And when you find this functional dependency violates BCNF condition, you need to check whether this right dependent attribute is a prime attribute. If it is prime, then you consider that functional dependency satisfies 3NF condition. Confusing, right? So basic idea is this. What should I say? Prime. Give me 1 second. Let me think. How can I explain this in a easier way? In the meantime, please read this slide. Oh, okay. So,
Is there difference with candidate key and prime attribute? Is there difference between attributes and
okay. So let's look at that example. So we have a student ID and instructor ID and department name. We have this table and student ID and department name determines instructor ID, and student ID determines, oh, no, left side should be instructor ID. Instructor ID determines department name. This is a functional dependency 1, this is a functional dependency 2. And what is the super key? What is the candidate key of this table? Student ID and department name. This is the candidate key, right? Why? Because if you know these two, then we know the last attribute. So this is the candidate key. And in this particular example, student ID is a prime attribute. Why? Because it is a part of candidate key. Department name is also a prime attribute, again, because it is a part of a candidate key. All right? So here, instructor ID determines the department name. This is not trivial. So the condition, trivial? No. Second, is instructor ID super key? No. Then we should check the last condition. Okay, so FD is a problem. The right side, the dependent, is the department name prime key? Yes, it is. So this table is in 3NF. What this means is every non-prime key, every non-prime attribute must be determined by super key, nothing else. So this is the rationale of 3NF. This is the key idea of 3NF. So here, instructor ID, is it prime attribute? No, it is not. Instructor ID alone cannot determine anything, and instructor ID is not part of this candidate key. So instructor ID is just regular attribute. It is a non-prime attribute. Then this instructor ID must be dependent on super key. The left side must be a super key. Still confusing, right?
Well, in this case, the IID isn't the prime attribute, is it okay?
You mean if instructor ID is
Not in the
Can-
prime attribute.
you mean instructor what if instructor ID is not a prime attribute? Currently it is not a prime attribute.
Then the 223 beta minus alpha. 하나만.
어?
이게 다 프라임일 필요가 없는 거예요, 굳이.
No. Please read this again. Every non-prime attribute, I mean every regular attribute must be determined by a super key. And if it is, I mean, if the right side is a prime attribute, then the left side doesn't have to be a super key. Usually the left side should be a super key. There is a BCNF condition. But to weaken that condition, we allow non-super key to appear on the left side only if right side is a prime attribute. Why do we allow this? So prime attribute is, kind of important, meaningful attribute. It is meaningful in a table. And if you add some additional attribute, that becomes a candidate key of the table. Okay? And it is very common. Suppose this is an important attribute. This is a very meaningful attribute. And if you add one additional meaningful attribute, they become a primary key. Okay, let's assume that. And since this is a meaningful attribute, some other attribute may determine. It may have some, association or relationship with some other regular attribute, and these attributes may determine this meaningful attribute. And in 3NF, we will ignore these functional dependencies. In BCNF, we do not allow because they are not super key. But in 3NF, if the right side is meaningful, if it is prime attribute, we don't care. We don't care about these functional dependencies. That's the key idea. If it is not still, if it still not makes sense, then I suggest you look at the midterm exams from the previous years and do some practice. And you will get better understanding, I believe. Right. Okay. The same example. We have these two functional dependencies. Do we have two candidate keys here? Okay. If we know SID and instructor ID, we know the department name. Because if we know instructor ID, this alone can determine department name. And by adding additional attribute, it doesn't hurt. So these two attributes determine department name. Okay. And on the left side, if we know these two, we know instructor ID. So this is a candidate key. That makes all attributes of this table a prime attribute. Every attribute in this schema is a prime attribute. Then any attribute can appear on the right side of the functional dependency. Give me 1 second. Anyway, so this left side is super key, this is not. But since this department name is a prime attribute, we don't need to decompose. That's the idea. But as you can see from this example, a table that satisfies the 3NF condition may have some redundancy. A typical example is this address and phone number example. So we have a name column, phone number, and address. And let's assume Alice and Carol are roommates. They are sharing the same phone number and they are sharing the same address. And in this example, what is the candidate key? If we know name and phone, if we know name and phone, we can determine address. Actually, if we know phone alone, we can determine the address. And also, if we know address, we can determine the phone number, because phone and address, they are tightly coupled. Anyway, so suppose we got these two functional dependencies, and let's check if this first functional dependency satisfies BCNF. What is candidate key? Candidate key seems name and address, or name and phone. There can be multiple Alices. Here we have two persons who have the same name, but since this second Alice is living in a different address, the first one, third one, they seem to be different persons. Anyway, so name alone is not a candidate key in this example, so we need to know name and address. Well, we need to know name and phone to uniquely identify a particular record. So this is one candidate key, and this is another candidate key. So name is a prime attribute, address is a prime attribute, also phone is a prime attribute. So even if address is not a super key, it is okay. Phone can appear on the right side because phone is a prime attribute. Therefore, we may have a table like this. And should we think this table has a problem? Does it have redundant information? No. Although we have these two yellow colored records, actually they are needed. If we eliminate that redundancy, then we will lose information. Alice and Carol are living in the same apartment. They are roommates. That information will be gone if we decompose it. Okay? And the next slide shows pseudocode for 3NF decomposition. It looks very similar to BCNF algorithm, except the third condition. Advantages to 3NF over BCNF. Why 3NF is better? It always preserves functional dependency. So by joining tables, we can correctly restore required information. But 3NF has some problems. It's not a perfect solution. We may have some redundant data, but this is not a real problem. This is needed information. And sometimes we need to store lots of null values in the table. Why? Let's do the example. I don't think I can come up with a good example for this particular example. Oh, here we have a null value here. How come we have a null? Okay. Consider these two functional dependencies. If we know address, phone should be determined. Okay. So if we know address, phone is determined. So every address has one single phone. Since this is not a smart cell phone, and if we know name and phone, we should be able to determine address. Can you store null value in name? In what sense? Null can be anything. It is unknown value. So null and specific phone number determines address. Even if we do not know name, phone can determine address. Just like address determines phone. It is one-to-one mapping. In that case, this table allows people to store null values in name column. I guess that is the meaning of this second bullet, second to the last bullet. But I don't think that is a good example to explain this problem. Anyway, sorry, I don't have a good example to explain this problem in my mind at the moment. Anyway, it is known that 3NF often suffers from lots of null values in the table. Let's move on. So we just learned two normalization theory. We have a couple more, but I don't think they are commonly used, so you guys can ignore it. We have false normal form, false normal form, and so on. Maybe we will talk about false normal form later when we talk about big data processing system. And false normal form is easy. I can just explain this. What false normal form means: if attribute domains are atomic, we say the table satisfies first normal form. If attribute value can have multiple values, like a first name, last name, then we say that table is not in first normal form. It has to be decomposed into first name and last name, something like that. And so the reason why we talk about this normalization theory is because we want to avoid redundant data so that we can save disk space. And also, when we update a data, we need to update just single record because there is no redundancy. And if we keep just single data, the data can be atomically updated. So consistencies can be easily guaranteed. But if you have redundant data, some data may become inconsistent with other data. And normalization requires to decompose unnecessarily combined tables. So by decomposing those mixed tables into multiple tables, you will have a clear relationship between those tables. And we have some more. So suppose you are developing a database application, and your first goal should be BCNF. You should eliminate redundancy if possible, and then you need to check the decomposed table can restore the original semantic of your application. then we say your tables satisfy lossless join condition. And also you should check you didn't lose any functional dependencies. So you shouldn't lose any meaningful functional dependencies in your decomposed tables. But if all these three goals are not satisfied, then you need to sacrifice storage space. You should allow redundant records and try to use 3NF. And this normalization theory is purely theoretical. So DBMS, like Postgres, does not provide any way of enforcing these conditions. When you design your tables, you should think of these conditions in your head, and then you need to design your schema. And nowadays, this normalization theory is not as important as in the past. So in the past, when you develop applications using relational DBMS, you are responsible for everything. So you can design database table schema. But nowadays, schemas are given. Why? In old days, you develop database application using RDBMS and you design your own schema, and then customers will insert data into your schema. They will insert data into the tables that you designed. But in big data systems, people generate data in the web, and they publish lots of JSON and XML those documents without any fixed schema. They have a bunch of various information without any fixed schema. So your system, your NoSQL platforms must handle these data. So you cannot apply normalization theory. You cannot enforce people to generate their data as you want. These random data will be given to you, and you need to somehow organize it. At that point, you cannot apply this normalization theory. So there is no schema in NoSQL, whereas in RDBMS, you have a fixed schema, and you can well design your schema using BCNF or 3NF. But in NoSQL system, there is no such a thing. Schema is not fixed. So suppose you design the schema R, and this R can be in a really bad shape. This table can be just one single table. Your schema can have just one single huge table containing all attributes from all different entities. Using normalization theory, using BCNF or 3NF, you can break the large table into small good tables. But nobody does this. This is a really bad way of developing. Instead, people usually use ER diagram to carefully design their schema, and then use this normalization theory to verify their ER diagrams are in good shape. There is another reason why this normalization theory is not important, but it is important for your exams. Otherwise, the exam will be too easy. Denormalization for performance. So, usually normalizations are considered good, but people intentionally ignore that normalization theory for performance reasons. Join is the most expensive operation in DBMS. So suppose you decompose those tables, and whenever user query comes in, you run join operation, multiple join operation. Then latency will be very high, and people will be unsatisfied. They will be unhappy about your application's performance, and they will not use it. instead, combine multiple tables and build a single large table. Then you don't need to perform join operation, although your application is going to use lots of disk space. If the performance is good, then people will use your application and people will be happy. So sometimes people intentionally ignore the normalization theory. For fast lookup, so maybe you can ignore the normalization theory when you design your schema. And there's an alternative. Suppose you designed good tables, well decomposed tables. You found that these tables are joined too frequently and that makes applications run slow. In that case, you can build a materialized view. What is materialized view? Materialized view is an intermediate output table. So periodically, you run join operation and generate intermediate output table and store that output table in main memory or disks. So later, when subsequent queries arrive, instead of running the join operation, you can just start from that intermediate materialized view to avoid the join cost. Okay? Okay, that's it. Any question? No question? Good. Then you are done with SQL part, and now let's look into internals of DBMS. We have only 50 minutes. Oh, really? Huh? Oh, 7? Oh, sorry. How can I do that? Edit? Okay, maybe I'll change it to yesterday. No due date. I should have posted in 6 weeks. Is it only 6 weeks? So, can you guys open it? Good. All right. So the next lecture will cover chapter 12 and chapter 13. So normalization theory is chapter 7, and we will skip chapter 8, 9, 10, and 11 for now, because this chapter 8 is about semi-structured data formats like JSON, XML, and they are very trivial. This chapter just explains why these complex data types were introduced. It is because of the World Wide Web, Internet, and people exchange documents in a standard format like XML and JSON. And I don't think this is really worth our time at this point. Maybe we will talk about this at the end of the semester when I introduce big data processing frameworks. And chapter 9 doesn't belong to this course. It introduces HTML, JavaScript, and so on. And I know that these HTML, JavaScript are covered in software engineering class and some other lab courses cover these topics. And I don't think this is a specific, this is needed for database systems course. And big data processing, we are going to talk about this at the end of the semester. And chapter 11 is about data analytics, data mining. What is data mining? Data mining is about finding some useful information from lots of data. So people store data in DBMS, relational DBMS, or big data processing frameworks, and data scientists submit some queries to find out useful, meaningful information from the large data set. The techniques are called data mining techniques. And there are many, people have developed a lot of heuristic and ad hoc data mining algorithms, but now they are all gone. Why? AI. AI is fast replacing those data mining techniques. So data mining techniques covered in chapter 11 will not be useful anymore. So we can completely ignore chapter 11. And instead you guys should take AI classes in third year or fourth year. Nobody is doing data mining anymore. Maybe I can give you an example about this data mining. So maybe I can introduce the goal of data mining. So in the United States, if you go to a large supermarket, then they place diaper, 기저귀, baby diaper, and beer bottles together in the same section. Why do they do that? It is because baby moms stay at home, and usually husbands go to supermarket and they buy diapers because their wives ask them to buy. And then if the supermarket place the beer bottles next to diaper, they found that these beers are selling selling very good. So somehow they found it. Somehow they found those information that can boost their sales. How did they find it? They analyzed people's purchase history, and they found that these young men buy diapers and beers together. So maybe if we place them in the same section of the supermarket, the sales will go up. That's what they found. So that is the goal of these data mining techniques, and that is why data are stored in storage systems called data warehouse. And OLAP stands for online analytical processing. So far we covered online transactional processing, OLTP. What we learned so far is called OLTP. So we insert the data, they should be atomic. Somebody search data, the search operation should be also atomic. We care about this atomicity and transactional concept, but in OLAP, we don't care about those transactions. Why? Those decision makers like the CEO, CHO, CIO, they make big decision, and their decision is based on analysis, and that analysis doesn't have to be accurate. As long as it gives some good amount of information, it doesn't have to be 100% consistent. What I'm saying is, suppose people purchase items from supermarket, so lots of data are accumulated. And when another person is buying an item in the supermarket, and he will place another purchase history in this database system. And that is OLTP transaction. And this OLTP transaction must be atomic and consistent always. But what about CEO? What about the manager of the supermarket? This guy doesn't care about this specific person's purchase. What he cares about is, among these purchase history, what is selling most? Even if this guy doesn't see the most recent transaction, that is okay. He just needs to get some approximate information about what items are selling better than others. So, online analytical processing scans most of the data without worrying about consistency. And OLTP transactions care about correctness, consistency, and they touch very small portion of the database system. They touch only single table or two table, and they finish very early, very quickly. Online analytical processing runs several hours or sometimes several days. So it is slow, and OLTP is very fast, quick. So it has very different purpose from OLTP. And so data mining is algorithm that finds meaningful information from bunch of raw data. And OLAP is how we run those queries in DBMS. And data warehousing is about how to manage those data in large data center. That's it. So I guess we can skip chapter 11. Any question about data mining? No?
What is the purpose of OLTP?
OLTP is about banking application. So you transfer money, and even if the system crashes, you should not lose the money. So it's about write operation. It's a write and read operation, and those write and read operations should not conflict with each other. If they conflict, then DBMS should resolve those conflicts and provide consistent view so that nobody lose any money. OLAP is usually read operation. I mean, 99.99% it is read operation. It just scans all data in their data center and then runs some data mining algorithm and return useful, meaningful information to help those decision makers. Okay. All right. So from today, we will look into how DBMS manages data internally. And the first part is about storage system, storage management. DBMS stores data in disks or SSD. Similarly, in operating systems, we have file system. For your homework, you need to create a SQL file, right? Those files are managed by file system. And both DBMS and file system manage data durably, which means even if you lose power, the data will not go away. They will stay. Even later, when you boot your machine, those files will be accessible. So it has similar goals. They have similar goals, but why do we develop? I mean, why people developed DBMS when there's a file system? That's the question that we are going to introduce. I mean, we are going to talk about in this chapter. Storage systems can be classified into volatile storage and non-volatile storage. Main memory is volatile. They lose data when they lose power, whereas SSD, hard disk drive, they keep the data even if power is switched off. And main memory and storage devices have their own performance characteristics. And I asked the GPT to draw this image. And I guess it's too much, but so when you consider whether you want to store data in storage or, I mean, hard disk drive or USB or flash-based SSD or main memory, you need to think about these performance characteristics. And we have a characteristic, I mean, performance metric called latency, and another performance metric called bandwidth. What is bandwidth and what is latency? Latency means how long it takes for a data from the source to arrive at the destination. This side, I mean, this lower side will be CPU, and this upper side will be storage device. Some devices have a higher latency. Some devices have low latency. Which is better? Low latency is better. And although this second device has lower latency, the bandwidth of these two devices may be the same. And also, this second device and third device, their latencies are the same, but some devices may have smaller bandwidths. SSD is electronic device, and it supports parallelism. So it can read and transmit multiple disk pages simultaneously. Then that device will have higher bandwidth. If the parallelism is low, then that device is going to have a small bandwidth. And when you consider performance, you should also think about the data source. If the data source has small amount of data to transmit, even if the device has very high bandwidth and low latency, the throughput will be small. So throughput is a metric from the client, and bandwidth and latency are the metric from the perspective of devices. Okay? Sometimes people are confused with bandwidth and throughput, but throughput is the metric for client, and bandwidth is the metric for device. And also you need to consider cost as another metric. If two devices provide the same performance, then you need to compare the cost of those devices and choose cheaper one. Give me 1 second. Can I finish this? Maybe. I should stop here. Any question? No? Then I will see you on Thursday. I don't know, Wednesday.